So, we are in our final lesson of Chapter 5, tackling the concept of independence in probability questions. And independence is a topic we've talked about before a little bit, and I'm going to remind you guys of what that means as we get things started here. So, first of all, before we answer this question, and I tell you how you tell if things are independent, let's talk about what it even means for things to be independent. Where would we have heard this word before? It was back in like chapter 1 when we talked about the idea of a conditional distribution. Conditional distribution where we were looking for if one variable had an association with another. So we said that two variables have an association if one variable, knowing the value of one variable, gives us information about another. We're careful not to say cause and effect. Well, if two things are independent, it means that there is no association. And if there's no association, knowing one gives us no info about the other. In like a very simple sense, if I flip a coin and flip a second coin, knowing the outcome of my first coin does nothing for me about my second coin. Earlier in the chapter, I talked about that roulette wheel where they show what the last spin was. Well, the spins are independent of one another, so knowing one doesn't help you at all with the other. Now, when we talk about independence in AP stats, you very, very rarely will be talking just from your gut on this. Like, oh, it doesn't seem like one affects the other. What you need to do is show mathematically that the events are independent. So there is a formula you will check to make sure the events are independent or if they're not. What you will do is find the probability of one of the events, probability of A. And if the probability of A is equal to the probability of A given B, this would mean that A and B are independent. So A and B are independent if this is true. Probability of A equals probability of A given B. You could also reverse it and do it the other way. Probability of B equals the probability of B given A. Basically what this means, I'll use the top one. So probability of A is the same thing as the probability of A given B. In other words, B happens. Well, okay, it's still the same probability for A. It doesn't tell me anything. All right? You have to be careful about not mentioning cause and effect when you do this because that's not what's going on. It's that one variable gives you no information about the other. So if B happens, that doesn't tell us anything about the probability of A. And we're going to look at the example from last time, which will be a really good one to kind of visualize this, which is that Diamondbacks example where we had the free tacos and we had the wins. I'm going to go ahead and put that table back on here, but you guys should look back in your notes and flip to that so you have that handy when we talk about this, or just recopy it when I write it down. Okay, so here's that table that you guys had from your last slides. I believe it's the exact same one that you guys already have written down. They asked us if tacos and wins are independent of one another. And again, you have to be careful when you talk about independence. It doesn't mean one has to affect the other. We're not talking cause and effect. We're just talking if one event gives us info about the other. So if we want to establish that these events are independent, if you start saying, well, yeah, the wins affect the tacos or something, just wrong. No credit. It has to be mathematically, and you do that using what's written in red right here. So what I will do to verify these events are independent, or if they're not, is I will find the probability of one of them. Doesn't matter which way you do it. Let's say I go for the probability of tacos. Probability of tacos is 30 out of 81, based on what I have written down right here. 30 taco games out of 81. Then what I'm going to do is I'm going to find the probability of the same thing, tacos, given the other events, given that you win. So, okay, they won. Does that tell us anything about the probability of tacos? And then if I know that they won, I would be looking at this guy right here. So my probability of tacos given win is 26 out of 41. You can look at those right there and see that they're probably not the same, but I'm going to go ahead and make them decimals anyway to make it easier to compare, and we can make a point about that. So let's talk about this first guy right here. There's a 37% chance in a random game that the Diamondbacks are going to win tacos, or that you're going to get tacos because the Diamondbacks scored 6 runs. And there is a 63% chance, 63.4% chance that the Diamondbacks, if they win, that you're going to get tacos. So in a random game, if you just walk in and said, hey, are we getting tacos today? That's when you score 6 runs or more. There's a 37% chance that's going to happen. But if you know they win the game, you look only at the games they win, that chance of getting tacos jumps to 63.4%. In other words, if you know they won the game, there's a greater chance that they scored 6 runs. Because those terrible games where they score 0 runs and 1 run, they probably didn't win in the first place. So if you know they win, your chance of getting tacos actually increases. Does that mean the win caused you to get tacos? No, it didn't. You could win by scoring 2 runs or 3 runs or 4. But they're tied to each other, and winning, knowing that piece, made it more likely that you would get tacos. You could have also opted to do these the other way. You could have done probability of win and probability of win given taco. It's the same logic. If you know they get tacos, there's at least 6 runs. And if you get 6 runs, you're probably more likely to win the game. Okay? Now, I need to actually answer the question because I haven't done that yet. What I would have to do to get full credit for this problem, because I've just shown some work. I haven't actually addressed what they said. I'm going to say something to the effect of, since the probability of tacos, which is 37%, does not equal the probability of tacos given wins, which was 63%, the events T and W are not independent. In order for them to be independent, you have to get the same thing. That means they're not independent, and it's because of what we talked about. If you win, you're more likely to have scored 6 runs. So 2 events can be dependent without one actually causing the other one. So you do not need causality to be able to talk about independence here. So this is a good thinking page right here, where you probably should pause the video and think about it for yourself a little bit. There's a difference in the 2 terms that kids get confused a lot, are the idea of mutually exclusive and independent. Mutually exclusive comes up in our OR style probability. Independent comes up more in our AND style probability. So when it says what is the difference here, maybe write that over here. Mutually exclusive comes up in OR, independence comes up in AND. But think about how you can fill out these tables. I usually give groups a few minutes to think about this one. So I'm going to go ahead and talk about the answer. Pause the video if you haven't tried it yet. If 2 events A and B are mutually exclusive, it means they can't occur together, which means that A and B up here is a 0. And then in the rest of the boxes are pretty easy. You can just use basic math to figure out what's going on right there. That's the only possibility there, that they cannot occur together. That's what mutually exclusive means. So mutually exclusive means they cannot occur together, which is no overlap. Independent, on the other hand, this one is usually a little tougher on kids to figure out. It goes back to that definition of independence. You can do it in either direction, but I'm going to do probability of A versus probability of A given B, and these need to be equal. The probability of A, I can pick out of my picture right here, it's 60 out of 100. So that's fine. I need to compare that to the probability of A given B. So if B is given, I'm out of this box right here. And it would go probability of A and B, which is this box, out of probability of B, which is 30. So essentially what I have here is like a little cross multiply problem, or you can just treat it like a decimal, make this a 0.6 right here. If you actually do that, that's going to be 18 for your answer. So this is going to equal an 18 out of 30. This box right here must be 18. Why? Again, if you find probability of A, that's 60 out of 100. A given B is 18 out of 30, which is also a 0.6. So it equals the right thing. And then from there, you can just fill out the rest of the numbers using your basic subtraction rules here, and you get your table. So independent means that one gives you info on the other. We just defined that on the last page, so I'm not going to make you write it down again here. But make sure you can keep those two terms straight. So review here of all this probability business that we've been talking about in this chapter. And you have to look at whether or not in an OR problem, they're mutually exclusive, and in an AND problem, if they're independent or not. If they are mutually exclusive in an OR problem, all you do is you add your two probabilities together. Done. They don't overlap, you just add them and it's over. If they're not mutually exclusive, you still add them up. But then afterwards, you have to subtract out the overlap, the stuff you double count, which is this right here. Again, if you do the two-way table strategy for OR problems, you don't have to worry about this step because you've already broken it into mutually exclusive boxes. But that is your basic setup for OR problems. Then we have independence right here. If events are independent, I flip a coin, I flip a coin. All you do to find an AND probability is you multiply the probabilities together. 1/2 times 1/2. Whatever events you want to think about, if they're independent, you just multiply their probabilities together. If they are not independent, or in other words, if they're dependent, you're still going to multiply. So you start out with the same first probability, but then what you do is you adjust your second probability. Like I did a marble example a video ago. If I wanted to get 2 blue marbles, I have 5 blue, 5 red. My first one is going to be a 5 out of 10, but my second one, if I don't put it back, is going to be a 4 out of 9. So you have to adjust that second fraction. And the way that you would do that is you would find the probability for your second event given your first events. So basically you have to account for whatever it is you already took out. I wouldn't get too caught up in symbols with these. What I would do is I would just think your way through it and you should hopefully be okay. So let's look at a few other smaller things right here. This next problem is actually a little bit different than what we've been doing here. So we have a test during the first trimester of pregnancy to decide if there's some sort of abnormality going on. Approximately 5% of these tests will be false positive. So what we're doing here is we're looking at 100 women, and we're saying out of those 100 women with normal pregnancies, what is the probability there will be at least one false positive? There's a 5% chance you have a false positive, okay? The first thing you need to do when you're doing some sort of probability question like this is acknowledge that the events are independent. So it's reasonable to say that each woman's test is independent. Okay, so each woman's test is independent, which means if we need to, we can just multiply their probabilities together and we're cool. We do not have to adjust. One does not have any sort of bearing or tell us anything about change the odds for another probability. All right, so that's the first thing. The other thing about this problem here is they're asking kind of a tricky question. What they're saying is, what is the probability out of 100 women, at least one of them will be a false positive? These words like at least or at most are tricky words that should like signal to you that you're going to use a little trick I'm about to teach you. At least one false positive is crazy because what that would mean is I would need to find the probability that exactly one woman out of 100 has a false positive. Then I would need to find the probability that exactly 2 women out of 100 have a false positive. And then I'd have to find the probability for 3 and for 4 and for 5 and for 78 and for 79 and for 88 and for 89 and for 91 and for 95 and for 99 and for 100. I would have to calculate literally 100 different probabilities to answer that red question. At least one false positive could be all of those options. Now that is awful, and it is not something you will ever be asked to do, because what we're going to do to answer this question is use our good friend, the complement that we learned about earlier in this chapter. Instead of finding all of this awful red stuff right here, 100 probabilities, think about what you haven't found in the red. What we haven't found is the probability of no false positives at all. So what you can do with a problem like this is find this guy, way easier than all that red stuff, and then afterwards, just do a complement to get what you actually cared about. So that's the basic setup right there. When you see words at least or at most, you're probably being set up to do a complement type of problem. So I need to find the probability that in 100 women, none of them have a false positive. That's what I'm being asked to do. Well, what's the probability for an individual, for one out of those 100 women, that they don't have a false positive? If 5% of pregnancies have a false positive, that means the probability they don't have a false positive is going to be 95%. That is woman number one. Okay? Woman number two is also going to need to not have a false positive. So that's a 95% for her. Woman number three is going to have a 95% chance, no false positive, et cetera, for each of those different women. So an easier way of writing this one out is to say 0.95 to the 100th power. I need the first woman and the second and the third and the fourth and the fifth and the 100th to not have a false positive. So if I multiply that out, 0.95 to the 100th power, it's kind of small. This ends up being 0.0059. So I've been purposely trying to color code this right here because this can be a little tricky to wrap your head around. The green guy, the probability of everybody being cool and not getting a false positive is less than 1%. But I didn't want the green guy. I wanted the red part or pink part right here, which is at least one of them being a false positive. So what I'm going to do to finish this one off is do the complement. I'm going to take 1 minus the probability of nobody having a false positive. And if you do that, it's going to be 0.994. So that's the probability that we're actually asking us for in the problem, which is all these other 100 options added up. So we talked about false positives and false negatives in the last example, but think again what this is saying. Even if for one person, there's only a 5% chance of a false positive, when you test a lot of people, sooner or later, like it's almost certain, we have like a 99.4% chance somebody will have a false positive. So most of the time when you go through some sort of testing for whatever, they're going to test you twice just to make sure that you're not one of those like false positive or false negative situations. Okay? So problems like this where you have to do at least or at most and do a complement are common, especially on multiple choice questions. So that's something you should expect to see on your chapter test. All right. Our next little problem right here is more of a trick question, kind of spoiling it for you in advance. We're going to say that for today, there is a 70% chance of rain in Maplewood, and then there's also a 70% chance of rain in Richmond Heights. What's the, for tomorrow, I guess. What's the probability it will rain in both towns tomorrow? So the word both kind of implies and. So if you see and, you would be like, oh, you multiply the probabilities, 0.7 times 0.7. But if you multiply them straight up, that is assuming that one event is independent of the other. That's not true. If it's raining in Maplewood, it is almost certainly raining in Richmond Heights as well. So basically, like if I was going to do this, if the probability for Maplewood is a 0.7 of rain, the probability of Richmond Heights, given that it's raining in Maplewood, is probably something like 0.99. Like it's actually really, really high because if it's raining in Maplewood, the town next door is probably going to be raining as well. There's always that situation where it's not the case, but it's pretty unlikely. So you cannot just multiply these together straight up because they're not independent. So we can't compute without more info because the events aren't independent. So be careful before you start multiplying stuff that it actually is independent. So otherwise it's like a trick question. This next slide, I'm not going to go over with you guys here, but it's kind of an interesting article right here. My face is covering it a little bit. But basically what it talks about is the idea that first name and last name are not independent of one another. So your first name and your last name actually have connections here. You see it a lot in names of like certain ethnic origins where like different first names and last names go together more often, even though they may not be the most common name in America separately. When you put them together, they are. So basically, it's an article about how your first name and your last name aren't necessarily independent. And then the final thing I'm going to do right here, this is unrelated as well to our main lesson right here, but simulation style problems are one of the toughest parts of AP Stats for kids. And I wanted to do an example of this here because there will be something like this on your next chapter test. So we have a girl who was a 60% free throw shooter last season. She wants to get better and she trains and practices and all that. And then in the first 3 games of the season, she hit 12 of her 16 shots, which is a 75% rate. So we want to see, based on that evidence, whether that's convincing enough that, oh yeah, she actually has gotten better, or could she still be a 60% shooter who's just got lucky in her first couple of games and had a sample where she did better than usual. Okay? That's the basic premise of this problem. Is the evidence from her first 3 games enough that we can be confident she's no longer a 60% shooter? So what we would do in a situation like this is design a simulation. And we would try to figure out, basically we could do something with a calculator like we did earlier in this chapter, where we would make it so she's still a 60% shooter. So maybe the numbers 1 through 60 would be she makes it. The numbers 61 to 100 or 99, whatever would be, no, 100, would be that she doesn't make it. And we would try to figure out if we make 16 shots happen, we would look to see in what percent of the time she got 75% or more. Could 75% happen in 16 shots, given that she's still a 60% shooter? So they went ahead and gave us a dot plot right here, and you can expect to see a dot plot like this somewhere on your Chapter 5 test. What you do with a picture like this picture assumes she's still a 60% shooter, and we have to figure out how rare what actually happened in real life is. So assuming that she is still a 60% shooter, how rare is it to get 12 or more of her shots correct, or to make 12 or more of her shots? So when you do a problem like this, you find what you got in the problem, but you always count more extreme than that as well. Because if you're going to be impressed by a 12, naturally you'd be even more impressed by a 13 or a 14 of her shots. And then what we're going to do is count up those dots. I count 14 right here. I might be off by like 1, but I'm pretty sure that's 14 dots. So in 100 simulations, 14 of them had a 12 or better, given that she's still a 60% shooter. Computer assumes she's still 60%, and they looked at what happens. So the probability, so assuming Ashley is a 60% shooter, there is a 14 out of 100, which is like 14%, obviously, chance. Move my face here. So there is a 14% chance that she could make, that's a really bad could make 12 or more out of 16 shots. So you have to think about what that means. If there's a 14% chance that she's still a 60% shooter, that's basically what we found right there. Is that high enough or low enough that we should be like, okay, confident she's actually better now? 14% is usually considered to be too high for us to be certain that we were wrong in our initial assumption. So there's a 14% chance she's still a 60% shooter, basically, is how you can think about that right there. And 14% is probably too high for us to be like certain. So what should we do? Well, we should collect a little more data. If she kept on shooting that and we had bigger samples, well, that tells us, okay, yeah, she's probably not a 60% shooter anymore. The most common cutoff for problems like this is 5%, but you can use 10% or 1%, and that can vary a little bit from problem to problem. But basically what you do is you figure out what happened in real life plus anything more extreme than that. And you figure out if that probability is low enough. If that probability, like let's say same exact situation, but instead of hitting 12 out of 14 shots, 12 out of 16 shots. She actually hit 14 out of 16 shots. Well, 14 out of 16 shots, that's 13 right here. She never got 14 out of 16. So the probability of that happening would be about 0 out of 100. And if I saw that, I would be like, whoa, she's gotten better. She's definitely better. There's no way that's going to happen, or it's very unlikely to happen if she's still a 60% shooter. But in our pink problem right here, getting 12 out of 16 was like kind of rare, kind of surprising, only a 14% chance of that happening. But that probability is too high to be certain. So that's how you use one of these simulations to analyze a probability. And it's something we'll practice in class as well, because it is something that kids do struggle with. But hopefully that makes at least a little bit of sense. And hopefully you understand this concept as well as that rest of that stuff we've talked about in this lesson regarding independence.